In the previous lecture, you explored about memory command. In this lecture, let's explore about sections command. Sections command is used to create different output sections in the final ELF generated. This is an important command by which you can instruct the linker how to merge the input sections to yield an output section. This command also controls the order in which different output sections appear in the final ELF file generated. By using this command, you also mention the placement of a section in a memory region. For example, you can instruct the linker to place the .text section in the flash memory region, which is described by the memory command. Let's see one example of sections command, how to use this command. So it all starts with the command keyword sections. This is a standard keywords. You have to write in all capital letters. And after that, this is a body. Sections command is used to create different number of output sections in the output file. For example, in this case, the output file generated will contain two sections. One is .text section and another one is .data section. This command instructs the linker to create two sections in the final output file generated. In this case, the output file is nothing but .elf file. The sections will appear exactly in this order. First, .text section will appear, followed by .data section. Let's take this example. This is one of the output section which we want to create. Here, this is a label of the output section. This label can be anything. It depends on you. You can give any name you want, but you have to follow some standard naming convention. This is the output section name. This is the body, and this gives the address information to the linker and the locator where to place this section in the memory. This is a combination of VMA and LMA, where LMA stands for load memory address and VMA stands for virtual memory address. And more on that we'll see later, how to use this syntax properly. But this actually gives the section placement information in the memory. This output section is used to merge all other sections of individual input files. How many input files we have got in our project? So we have got 3 input files, isn't it? Main.o, led.o, and we have one more, startup.o, as I described in the earlier slides. And each object file contains its own different sections like text, data, BSS, constant. By using this output section, we are going to merge all sections of input files like this. Let's use this text section to merge all ISR vector section of all input files. Merge all .text section of all input files and merge all .ro data section of all input files. After that, just mention the address here where those sections should go. And after that, let's use another output section .data to merge all data section of all input files. Let's edit our linker script to create some output sections. I'm going to write sections here and I'm going to open the brackets. The first output section, what I want to see in the output ELF generated is, let's say, .text. This is the name of the output section or label. You have to give colon and its body. Here, let's merge text section of main.o, led.o, and startup.o. How do you write this? You can use one shorthand notation. So you can mention something like this. You can use .text of all input files. You can use the wildcard character here, star, asterisk you can use. This denotes consider .text of all input files. Instead of writing dot text of main.o, ld.o, startup.o, you can use this shorthand notation. If you again refer to this diagram, this explains storage of final executable in code memory. The initial code space must contain the vector table. After that only the .text section should appear. We have to follow this order. Otherwise, our application will not work properly. That's why what you have to do is you have to first merge the .isr underscore vector section. .isr underscore vector of all input files. You can use wildcard character. For this application, it is not required because there is only one ISR vector section. But that's okay. This is a generic statement. After that, according to our diagram, we want to place .ro data. Let's do that. Star of .ro data. This output section comprises of all these individual files section. We just created one output section, that is .text. Now you have to decide where you wish to store this section in the memory. That means you have to mention two memory regions for this section. One is VMA and another one is LMA, where VMA stands for virtual memory address and LMA stands for load memory address. Before that, you have to ask one question. So do you relocate this section in your startup code? No, we don't relocate this. This is going to be stored in the ROM space. ROM in our case is flash. It doesn't have any relocatable address. That means VMA and LMA are same for this section. That is flash. This section should go to flash, and flash begins from here. That's why next step is you have to mention the section placement by using the symbol greater than. What you do is give a greater than symbol, and here you have to mention the VMA. Then use the command at greater than symbol, give space, and now mention the LMA. VMA in this case is flash and LMA is also flash. Once the linker sees this, what it does is it generates absolute addresses for this section, and that addresses fall in the memory region what you mentioned in the VMA. After that, the linker also generates load addresses for this section. That addresses fall in this memory region what you mentioned after the at command. Don't worry. So again, when we disassemble the final executable by using disassembly tool, you can understand more. In this case, both VMA and LMA are same. You need not to write something like this. You can just omit this. So you can just mention like this. This means that VMA and LMA are same. Let's create the next section, .data. And again, I'm going to merge data sections of all the input files here. The .data section is relocatable, isn't it? This must be stored in flash, but the startup code has to copy this section from flash to SRAM. That's why the load address is fixed, that is flash. In the flash, first this section will appear, and right after that, this section will appear. That's why you have to mention load address as flash. What about the VMA? And the VMA in this case is SRAM. When linker sees this, so it will generate load address for this section, which falls in flash right after this section. But the absolute address of this section will fall in the memory region SRAM, which starts from this memory location. I will show you practically, so when we disassemble the code. That's it. We created two sections. This is for initialized data. What about uninitialized data? That we call as BSS. Let's create one more section, BSS. And again, this is nothing but collection of all individual BSS sections of different input files And as I said, this will not get stored in the flash. That's why it has only VMA. So it doesn't have any LMA. VMA is nothing but SRAM. We just created a linker script which can generate 3 output sections for the final executable. And we have to keep improving this linker script. This is not final. In the next lecture, we will explore one more important concept of the linker script, that is location counter. And I will cover this in the next lecture.